Today I would like to refresh your mind about semiconductor physics, very fundamental ones, and then we go for diode, the simplest analog device. Actually, all those come from microelectronics. So if you have further questions, you can go back to read your microelectronics in good enough detail. Here I would like to show you the periodic table of the elements. You can see from the smallest one to the largest one. Actually, for semiconductor, we only focus on this column, on the elements in this column. Why? Because they have the so-called diamond structure. So it is really, really strong, really robust. And also, it has some kind of very fantastic properties. We call it semiconductor. It means the conduction is between conductor and insulator. All right? And after doping, we can increase the conductivity substantially. Even better is that by doping, we can have N-type and P-type semiconductor. And when you combine both, N-type and P-type, you will have the simplest device called diode. And diode can help us to conduct current in one direction, but stop current in the other direction. It is quite useful for our analog IC design, or for all kind of analog circuit design. Anyhow, I would like to show you this. From here, the smallest one is carbon, tan. But how can I say, carbon is quite easy to be formed, okay? So unless you use some kind of carbon chemical, otherwise, carbon itself is not so good for semiconductor usage. So we focus on the second, silicon. Okay, so till now, silicon is the, how can I say, most used element for semiconductor. And luckily enough, I guess silicon also dominates all the elements on Earth. It has the most value. Okay, silicon. Why? Because all the rocks, all the sands, actually are made of silicon. So we have plenty of silicon. You don't need to worry about in the future. Maybe we don't have silicon for semiconductor use. No. Unless you use out all the Earth. Otherwise, we have plenty of silicon to be used. It's very good because it means silicon is the cheapest element on Earth for semiconductor, right? And how about that? How about the others? Germanium, it's also the property actually. For conductivity, germanium is better than silicon. However, the leakage current is much more than silicon. Okay, so you will increase the power consumption, and also we don't have so much germanium like silicon on Earth. So anyhow, silicon is the best for the main body of our semiconductor. However, for pure element, usually it is useless. Okay, just like humankind, you can see if you have hybrid, 混血, okay, you can see usually the next generation perform much better than the first generation. Yeah. So again, one man came from Kenya, got married with a white lady in where? In United States? Anyway, okay, and gave birth to a hybrid child called Obama. Then maybe 20 or 30 or tens of years later, he became the first black, maybe hybrid president for USA. Yeah. Anyway, anyhow, for pure silicon, actually, I promise you, almost useless, because the conductivity is much, much less than conductor. How much less? Usually, maybe from, the difference is 9 to 12 order less than conductor. So what can you expect from such kind of semiconductor? Pure semiconductor, useless. Okay, but to enhance its property, its performance, we need to do doping. To dope the so-called impurities, 杂质. Okay, so what is the definition for impurity? Different from the original atoms. That is the definition for impurity. We have two kinds of impurity. One kind, we call them acceptors. Because for such kind of diamond structure, they have 4 covalent electrons, 共价电子. Okay, so they have 4. But how about here, boron, 硼? It has only 3. And the most stable structure for such kind of chemical, actually, you need to have 8 to get the most stable state for such kind of combination. All right? But 4 plus 3, it means less than 1. 7, less than 1 less than 8. So it means it can accept 1 more free electrons to construct, to generate such kind of very stable structure. So we call it acceptors. To accept what? Free electrons. Okay? And the other kind, we call it donors. Oh, you can guess. For donors, they have 5 valence electrons, right? So it means what? 5 plus 4, it means 1 more than 8. So after combination, 1 extra free electron will be released. So they can donate what? They can donate free electrons for what? For conduction. Okay? That's it. So we call it, what's the matter? Something wrong. All right, let's go ahead. This is some kind of, sorry. For donors, they can donate free electrons. For acceptors, because they can accept 1 free electron, right, for each atom. So it seems there is a hole to trap, to accept 1 free electron. So we call it hole. Okay, sorry, HOLE, 一个洞, 电洞. And here, free electrons, 电子. Okay, allow me to show you the intrinsic structure for such kind of semiconductor. Intrinsic means pure, 纯粹的. Okay, pure silicon, useless. But from the very beginning, you need to have such kind of pure semiconductor, then dope impurities to enhance very much the performance. So from the very beginning, you can see there is a very simple model called Bohr model, Bohr 模型. Actually, it's incorrect, but much easier to understand for students. So anyway, allow me to introduce such kind of not so correct models for you. Bohr model, you can see that is the core of the atom. Yeah, it has protons, neutrons, 质子, 中子. Anyway, out of the core, we call it nuclear. Okay. Yeah. Anyway, 原子核. Out of that, we have electrons. But the most active one are the outest, okay, peripheral one. So for inner electrons, actually they don't have any kind of how can I say activity, during combination with the others. So the most active ones actually are the outer ones. We call it valence electrons, 价电子. So this is the Bohr model for silicon. Okay, it has 4. But how to generate such kind of silicon crystal, 细晶体? Yeah, actually, each one needs to have 4 neighbors because I have 4. All right, everybody has 4. We can share with each other. So I share my one just like this. I have 4, right? I share this one with you. You share the other one. So totally, I have 8. You have 8. Everybody has 8 to achieve such kind of the most stable structure for crystal. That is very good. All right. So we have quite many presentations for such kind of crystal structure. Actually, it is a 3D one, a 3-dimensional structure. All right. So actually, it is not so good. If you can imagine, you have a pyramid, 金字塔, okay? In the middle, you have 1. So to the 4 corners, you have the other 4, okay? It's just like a diamond or a pyramid, as you like. All right, anyhow. But it's very hard to draw such kind of 3D diagram, right? So we just squeeze it to become a 2-dimensional one. It's incorrect. It's incorrect. But again, it's much easier for students to understand. So usually we are happy with such kind of wrong structure. Okay, but you need to remember that actually it is 3-dimensional ones. Oh, just like this. Okay, as I mentioned. Anyway, we have 2 fingers. It means what? For each bond, a covalent bond, 共价键, it contains 2 electrons, valent electrons. But I have only 1 here, and the other one belongs to you. That's it. But can you distinguish which one is me, which one is mine, which one is yours? Sorry for that. All the electrons, they look exactly the same. So we share 2 electrons with each other, but we don't have any idea which one is my son, which one is your daughter. Nobody knows. Okay, they are exactly the same. So you can see this structure. Oh, that structure is the same. Yeah, I have 4 bonds. For each bond, 2 electrons. Again, this or that is only easier to see, easier to plot, easier to understand, but actually it's totally incorrect. All right? Even if you go back to Bohr model, is it correct? No, it's totally incorrect. From solid physics, solid state physics or quantum physics, you will see, yeah, we call it electronic cloud, 电子云. Okay, for each electron, it has its own quantum state. Okay, for different quantum state, actually, the distribution, we call it PDF, probability density function, 密度, 几率密度函数. Okay, actually is totally different from here to there to there. Okay, so this is some kind of dynamic representation. You can see, wow, the higher density means what? The more probability the electron will show here. Okay, that's it. And it's almost impossible to predict if currently the valence electron is here. How about the next moment? Where will be it? Where it will be? Nobody knows. Yeah, we have the so-called uncertainty. Only uncertainty or something? Yeah, maybe. Pauli uncertainty theory. Pauli 测不准原理 anyway. Okay? So it's really hard to understand through quantum physics. Anyway, anyhow. Just keep this in mind. That is a correct model, but it's really hard to understand. Okay? So we will be happy to stay here to pretend it is correct, but actually it is not correct at all. All right? But anyway, with such kind of wrong model, not only for atom, not only for crystal, we can explain the semiconductor properties much easier than that one. So we are happy to show you the wrong models, but to get right idea, 用错误的模型来获得正确的概念。Anyway, anyhow, for such kind of crystal, actually, it is the so-called anisotropic, 非等向性. It means what? If you look into the crystal in different direction, not only the structure is totally different, but also the property is different. For example, if this is the crystal, I look into this direction or reversely, I promise you, the conductivity is not the same. Wow. Okay? In this direction, in that direction, not the same. Even in this direction, then go back. Sorry for that. The conductivity is not exactly the same. The property is not exactly the same. Some kind of something unbelievable, but it's true, again, from solid-state physics. Okay? So, the orientation of the crystal, or we call it lattice, 晶格, is very important. 它的转向, 它的方向. So Chinese or Taiwanese, they believe in feng shui, right? That is, it makes quite much sense for semiconductor. You can see, even for TSMC or UMC, they get wafers from the other company. They don't generate wafers by themselves. They buy wafers from the other companies. Okay, but the wafer company need to show the orientation of the wafer. If you rotate the wafer, then the yield will be down. Yeah, very, very substantially. So you need to be very careful the orientation of the crystal. From one direction, you can see, wow, it is you can see a very beautiful hexagonal structure, 六角形的结构 hexagons. Wow, really beautiful. Okay, for each stick, it means one bond. One bond means what? 2 electrons. So you can see, wow, 2 electrons here, 2 electrons there. Okay, wow, just like the two eyes of the duckling head. Oh, so for that, there is another joke. If your parents sell such kind of Dongsan duckling heads, then you may be very interested in TSMC because they fool around, they play with such kind of duckling heads every day, every night. Yeah, you had better go to TSMC to make much more money than this. Okay, and again, from some kind of quantum physics or solid-state physics, actually, the energy of the valence electrons, they are not exactly the same. From the very beginning, yes, they are the same. We call it Fermi-Dirac statistics. 佛米能阶. Okay, if the condition is at 0 degree, okay, oh, this is the absolute temperature instead of Celsius of 不是摄氏也不是华氏 ，OK， 它讲是绝对温标 ，Yeah， 0 degrees K means what? Okay, minus 273.16 degrees Celsius. Anyway, anyhow, without any temperature, it means everybody stand still. No movement. Everybody get exactly the same temperature, the same energy, sorry. Here, you can see T equals 0 degree K here. But if you increase the temperature, then the atoms in the crystal, in the lattice, will begin to vibrate. For such kind of vibration, go back to the wrong model here. The nucleus, the cores, don't stand still there, right? They try to behave badly. They try to shake their body. So you can see if they shake in this way, then the atoms here will be speed up in that direction. Okay? So you can see after vibration, the energy of all the electrons will be totally different. It depends on the directions of the movement, of the nuclear movement. For example, if the nuclear goes in this direction and the valence electron go in different direction, then after collision, not real collision, okay, after some kind of physically, not physically, non-contact, okay, collision, then the free electron is very, very small mass, much lighter than the core. So it will be speed up very much. Okay? On the contrary, if they move in the same direction, so only for that, the movement of the electrons will be slowed down. Anyway, just like you play tennis against the wall, right? If the wall can move further, your balls will be sped up. If the wall moves backward, your ball will be slowed down. That's it. So after vibration, you can see all the electrons will have different energy. So that is the most fundamental one. Fermi level will tell you, 50% of the electrons will get higher energy, and the other 50% will get lower energy. That's it. And this is some kind of equations for Fermi Dirac they derived in the past. Please, I'm not your teacher for such kind of quantum physics. Forget about it. But I do my best job for you. I show you the equation, and I would like to highlight that this term, exponential, that is really, really, really important. So after vibration, after you increase the temperature, you can see the more temperature, you have such kind of, we call it exponentially decay, right? Or exponential decay. Anyway, here, over there. It means what? The higher temperature, it means, the skirt, 裙摆, or the tail of such kind of exponential approaching infinity. Okay? Exponentially. But never mind, even with low temperature, just like here, the tail still approach infinity. But with much less probability. The higher temperature. So you can see, if you have some kind of barrier, how can I say? Barrier, 能量障壁, okay? You can see some of the electrons will go beyond the barrier to do something badly or something good. I have no idea. Okay? Yeah. But the higher temperature, the more electrons can go beyond such kind of barrier. Remember this. And exponent, the total number of the electrons can go beyond the barrier will be exponentially increased through the increase of temperature. Got it? Don't ask me why, because I show you this. That is the theoretical equation for you to refer, and please pay attention to here, especially the exponential term. Really, really important for all the fundamental semiconductor physics. Anyway, let's go further. And right now, I would like to show you we have three kinds of materials on Earth according to their conductivity. One we called conductor, the other one we called insulator. Okay, and in between we have semiconductor, partially conductive. That is, it means. All right? So for insulator, 绝缘体, it means what? For the quantum states, the conduction band here, and it means free electrons should be here. All right? And where is the valence band? Oh, valence electrons there. Here is a huge gap. So it means what? It's really hard for such kind of valence electrons to get high enough energy to become free. That's it. So for insulator, you have almost no electrons. But don't tell me 0 electrons. No. Why? Because unless at 0 degree K, otherwise, according to such kind of exponential decay property, never mind how high the energy gap is, you still have some or very few, even for the red one. Okay, you still have very, very few valence electrons can get high enough energy to go beyond the energy gap to become free electrons. Okay, that is another ugly truth for you. Nothing is perfect. Never mind what kind of insulator you have, I promise you, there will be some free electrons to conduct some current. Very few free electrons to conduct very few current. But don't tell me 0 current. It doesn't make any sense. I don't buy it. It's totally untrue. Okay? That is the definition for insulator. And how about the conductor? Oh, luckily enough, the conduction band and the valence band, they overlapped with each other. Congratulations. It means what? By nature, all the valence electrons become free electrons because they are overlapped. All right? Congratulations. Metal dominates the conductors. And then in between, you can see that is for semiconductor. The energy gap is not overlapped, but much smaller than insulator. Okay, so it means what? Some portion of the valence electron will get high enough energy to break through such kind of energy gap to become free. Bingo! Anyway, if you set free one valence electron to be free, then ideally there will be a hole left, a vacancy. Okay, because here for the atom, for the lattice, you have only 7. Originally you have 8, but one gets high enough energy to be free, right? So right now you have only 7. What you can do? Try to figure, oh, there is a weak free electron, so I would like to capture it. All right? So we call it, there is a vacancy. 那边有个空洞. If you go to United States, for the hotels, motels, and everything, if they in front of the hotel, usually they have vacancy. It means, oh, they have free rooms. They have halls for you guys to fill. Okay? Anyway, how many electrons to be free, it means exactly the same number of holes will be left here. Okay? So, if n means the number or the density of free electrons, it means negative because free electrons are negative. Okay? And then we have H for holes, right? The number of holes or the density of holes, as you like. By nature, I mean for pure semiconductor, they should be equivalent. Okay? So again, allow me to tell you that how to generate free electrons and free holes, the usual way is by thermal energy. It means by temperature. If you increase the temperature, you will get more free electrons, more free holes. If you like us, you will make it happy because they can conduct current for you. Okay? So to conduct more current, you had better heat it up. But don't burn it. Okay? 不要把它烧掉. Anyway, the more temperature, the more free electrons will be generated. And again, the same number of free holes will also be left. Not only the free electrons, but also the holes can help you conduct current. And later I will show you the conduction will be summed up, okay, instead of cancel each other. No, they can help each other to conduct more current. But thermal energy is not the only way to generate. Oh, we call it thermal generation because such kind of free holes and free electrons generated by pairs, 一对一对的产生, okay? And through temperature, we call it thermal generation. But thermal generation is not the only way to generate free electrons and holes. We can generate all those by kinetic energy, 动能. If you hit your semiconductor configurations, you can help it to generate more electrons and holes to increase the conductivity as you like. But it doesn't make any sense. Okay, how hard you can hit? Don't shit me. Okay? Only if the kinetic energy is greater than or equal to energy gap. Yeah. It can help you generate free electrons and holes in pairs. And then, not only thermal or kinetic energy, but also what? Photo energy, 光能. Okay? If you inject the light to the gap, it can also help us generate electrons and holes. But the energy of the light, or we call it photons, 光子, needs to be exactly the same as the energy gap. Lower, impossible. Higher, also. Higher, impossible either. Okay? It needs to be exactly the same. Wow, it's really hard, right? So usually we expose this to white light. So for the spectrum, light spectrum, 光谱, you can see some of the black lines because white means from the very low frequency to the very high frequency. Yeah, that is the definition for it has everything from the very low to the very high. So we call it a white light spectrum. After expose this to white spectrum, to white light, you can see some dark lines. Okay. For each line, it means it is exactly the same, not only for the valence electron, that is the smallest one, okay, but also for all the others. Okay? For this one to be free, you need the smallest energy. And then higher energy, even higher energy. So you have some dark lines, but it is very specific to this atom. For different atoms, see, for this, for that, for anyone. the Bohr models are totally different. So it means after you expose all those atoms to the white light, they will generate totally different black night spectrum, 黑线频谱, 黑线光谱. Okay, so you will know exactly what atoms they are. And this is a very useful way to detect drugs. We call it 质谱仪. I have no idea. Yeah, some kind of instrument to vaporize the chemical to become atoms, then exposed to the light. Then you will have quite many black night spectrums. Then you will know the composition of the chemical. Okay? Crack. Yeah. Marijuana, blah, blah, everything. 抓毒品的好办法. Yeah, anyhow. So keep this in mind. All those thermal energy, kinetic energy, and light energy, photo energy, can help us generate electrons and holes in pairs. Again, N equals P for such kind of pure semiconductor. Okay? Yeah, this is what I told you. The number of electrons equals the number of holes. All right? Now, because the electrons are free, so they can help you carry current. But how about the holes? Holes means vacancy. It means nothing there. Just like, okay, right now, here is the vacancy. No student here in the seat, right? So, can the hole or can the vacancy move by itself? No. We passed the ghost months already. Okay? If you see, the chair, the vacancy can move by itself, there must be something wrong. Some ghost over there. It doesn't make any sense. Okay? So how can the vacancy, how can the hole move? Very easy. The other students to fill the hole. So you can move here. But for the others, if they close their eyes, when they open their the free vacancy move over there. Okay? Yeah. So you need to be very careful. Holes cannot move by themselves because there's nothing there. Nothing. Can nothing move? No. Only the other thing can move, can feel nothing. And we pretend to think, the hole can move by itself. No. It is moved by the others. By the others what? By the other valence electrons. Okay? So you can see, for free electrons, they are free men. They can move anywhere as they like. I mean, they can move easily. And how about holes? They need to wait. Somebody to fill the vacancy. So it's much harder for such kind of hole movement. Okay? So we have mobility. Mu. Mobility, 移动度. Okay? Mobility for electrons and mobility for holes. You can guess. N-type mobility is much higher than P-type mobility. How much higher? Usually 2.5 to 3 times higher. Okay? I explained already why holes is much harder to move because they need to wait for the other valence electrons to fill the vacancy. And we pretend the holes move by themselves because it is easier for you guys to think. Okay? Yeah, anyway, we have thermal generation, light absorption, blah, blah, blah. Sorry. Yeah, it is some kind of... Okay. Oh, okay. Forget about it. Some problem with the links. Yeah. Okay. Here I would like to show you and the density of electrons, P, the density of holes should be exactly the same for pure semiconductor, or we call it intrinsic semiconductor. So we have this Ni. I means what? Intrinsic. Pure. What does it mean? Okay, what it means, pure. That's it. But don't ask me why it becomes such complicated. Yeah, in the form. Sorry for that. It is derived, again, from quantum physics. As an IC design teacher, I only need to help you fully understand the behavior. Okay? Yeah, but so I will be more than happy to explain the so-called behavioral models to you, but not the theoretical model. It is really complicated to derive, to understand. Okay, let's go ahead. So you need to be very careful. Yeah, free electrons, red dots, and ions, just kind of blue holes. In numbers, they are the same, 1, 2, 3, 1, 2, 3. Okay, that is for intrinsic semiconductor. Yeah, we have thermal generation, that's what I mentioned. The other problem is, as I told you, this is incorrect. We need to go back to refer the Fermi-Dirac model. That is the correct one. Anyway, anyhow, I told you, never mind how large the gap is, we usually, according to Fermi level, yeah, we never mind how high the energy gap is, we still have some portion here to get high enough energy to be free for valence electrons. So it means what? Only if the temperature is there, we will always have some portion of the electrons, valence electrons, to get high enough energy to be free. So what does it mean? You just put your semiconductor here, then wait for long enough. More and more, valence electrons will be free. Okay? So in essence, the number of hours will be less. So it means what? At the same temperature, according to thermal generation, you will get more conductivity by waiting. Does it make any sense? So, my iPhone is the core of my iPhone is made of semiconductor chip. I don't need to do anything. I buy an old iPhone here, then wait for a long time. Yeah, it will become it will change its type from iPhone 6 to iPhone 11 because it can run faster and faster and faster by waiting. Does it make any sense? No. According to aging, 老化, it will run slower and slower instead of faster and faster. But according to thermal generation, only if there is any kind of temperature higher than 0 degree, then some portion of the electrons will be set free. So in theory, the conductivity of the semiconductor will be increased by waiting. But it violates our intuition. It doesn't make any sense. The conductivity, never mind how long you wait, will be still the same. So we need another reverse mechanism to balance such kind of conductivity. So we call it recombination. That is another reverse mechanism. But how? Okay, very simple. Again, the free electrons, after collision, the so-called collision with the vibration of the atoms of the lattice, some electrons will be speed up again. Yeah, if they collide head to head in reverse direction, the free electron will be sped up. However, in the same direction, then the free electrons will be slowed down. Okay? In this way, again, the energy for free electrons won't be exactly the same. According to normal distribution, yeah, you can see, okay, this is good for free electrons. Okay? Yeah. So you can see some of the, to the left, never mind how high the temperature is, you can see some of the free electron will have almost zero energy. Never mind how high the temperature is. Some with very high energy, some with almost zero energy. Okay? So this is the definition for weak free electrons. It gets very few energy. In this way, if there is a hole nearby, the hole will try to capture. Just think, okay? Pretend it has the capability to capture not only the valence electrons, but also weak free electrons. You can see, if this hole capture only one free electron, they cancel each other, also one by one, or by pairs. 它们成对的消掉. Okay? So we call it recombination, 重组. So never mind, by thermal generation or by recombination, all happens in pairs, one free electron, one hole, to be generated or to be killed. So I promise you, N equals P all the way. All right? So you can think, by intuition, if at the same condition, the same temperature, blah, 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 the conductivity will be the same, right? No more, no less, by waiting. So it means what? The rate for generation should be exactly the same as the rate for recombination. Okay? That's it. That is our mother nature, beautiful nature. They balance all issues by themselves. 他们会自动平衡哈。Okay, anyway. Yeah. But how the free electrons or the so-called free holes help us to carry current? They have two mechanisms. 有两种机制. One is called diffusion. The other one is called drift. Okay, well, what is the difference? Okay, allow me to show you. Diffusion. Show you this. So it means what? From high density toward low density. That's it. The more gradients, the more tendency for diffusion. Okay? Okay? That's it. 浓度差越多，扩散力道会越强。Proportional to. Okay? The diffusion speed is proportional to the gradient of the density. So here is some kind of diffusion. Never mind for Hall diffusion or for electron diffusion. For example, this is for Hall. Okay? And this is the density of the holes. As I show you here, from the high density towed, diffuse to the low density area. So you can see, if you come here, high concentration here, low concentration there. So the holes will diffuse to the right. Right means positive direction for X. Right? But what is the gradient? 它的梯度是啥？ The derivation, the differential of the slope. The slope of the density means the derivation. You need to derive it here. So the whole current density is proportional to this, but with the negative sign. Because here the slope is negative, but actually the direction is to the right, is to the positive, right? So we need to get one minus sign. Minus means positive. Okay? 因为这边的斜率是负的，可是它是往正的方向走，所以我们要加个负号，让它负得正。That's it. And you can see for the holes, they carry how much charge? Exactly the same as electron. One electron leave, one hole left, right? So the charge for hole or for electron is the same. Okay? So you can see, oh, I am proportional to this, to that. The proportional constant, the proportional coefficient, we call it diffusivity, 扩散度。那是一个比率常数 right? If I told you, oh, y is proportional to x, then we can write y equals ax. A is the proportional constant, right? And here, dp is the proportional constant for Hall diffusivity. And this is the reason why we have P. Okay? Exactly the same, you can explain for electrons. However, if you have more electrons here, less electrons there, so the electrons will diffuse to the right. But the current should be reversed to the left because electrons are negative. They move to the right, it means the current is to the left. Okay, so we don't need such kind of minus here. That is the only difference for derivation. That's it. And you can see how much in difference. The whole diffusivity is 12. The electron diffusivity is 34. Almost 3 times larger. A little bit less. This is the reason why I told you. But why? Again, how can holes diffuse to the right? They need to wait valence electrons to fill them to the left. Got it? They still need to wait. They cannot move. They cannot diffuse by themselves. That's it. So it's harder for the hole to diffuse or to drift. Okay, that is the definition for diffusion. So for diffusion current, you need to be very careful. For hole diffuse to the right, the current is to the right. Okay? For electrons diffuse to the right, as I mentioned, the current is to the left. Got it? Okay, let's go ahead. Drift. What does drift means? Again, for free electrons, they can move freely in the outer space. No. In the lattice. But they will always collide with the lattice vibration, with the atoms, with the cores inside. Okay, 因为那个晶格里面的原子会震 only if there is any kind of temperature. Yeah, through such kind of collision, you can see, how fast the free electrons can move. I mean, for speed, to my memory, at room temperature, about 100 kilometers, but not per hour. Just like our car. No, per second. Wow! So it means what? If you shoot one free electron from Taipei, within 4 minutes, it will touch the end of Taiwan. Okay? Within minutes, it will reach Indonesia. Yeah. And then, penguins. In South Pole, they can move so fast. But unluckily enough, at room temperature, the collision frequency for free electrons with the lattice is 11th order of 10. So frequently, they need to collide with the atoms. Okay? So with collision, the direction of the movement will be changed. Okay, blah, blah, blah. So that is the so-called drift, 漂流. Why? Because, the first physician found such kind of drift mechanism. Actually, he or she, just like Shanghai Sheikh, has some kind of cordial time, is spent at the riverside and watch the leaves on the top of the river, right? Why? The leaf, the small leaf. Okay, and this is the river stream, 流水. Okay, downward, but it figured out that the leaves don't move directly along the stream. No. Why? Why? For big leaf, it just follows the flow, the stream. But for small ones, zigzag. Why? According to air temperature, many of the molecules of the air collide with the small leaf to the right, to the left, are not the same, right? To the top, to the bottom, not the same. So, two mechanisms for the leaf. One is the direction of the flow of the stream, and the other is the net collision of the air molecules with the leaf. So it moves. It is called drift. That's it. Okay? So, where is drift? Where is drift? I'll forget about it. Yeah. Anyway. So again, the electron velocity is proportional to the electrical field, right? Your speed is proportional to the magnitude of the E, electrical field. 你的速度跟你的电场是成正比的。Again, the proportional constant, we call it mobility. Wow. Here, mu n, the mobility for free electrons. Similar definition for Hall. The drift velocity for Hall is mu p. And you can see, wow, mu p only 480. How about mu n? Almost 1,350. If this is by 4, it will become. So again, very close to 3 times higher. The mobility here than there. Why? Again, the Hall cannot drift by itself. It needs to be filled by valence electrons, by weighting. Okay, that's it. But if you divide this by that, and you divide this by that, you will see they are exactly the same. Oh, it is very famous. A very famous equation found by Einstein, Albert Einstein. So Einstein is so talented. He not only created the so-called the so-called relativity, but also Einstein equation, blah, blah, blah. Many of the famous equations, famous phenomena found by Albert Einstein. Einstein 是个聪明到极致的家伙，发现了非常多的怪现象。Exactly the same. Okay, so it means here. Not only the ratio is exactly the same, but you can see, the thermal voltage, equals the thermal voltage. Wow, it's really fantastic. Really fantastic. The same for holes and electrons. But intuitively, they should be the same because the holes, again, need to be filled by the other electrons. But by valence electrons. Never mind, free or valence electrons. They are electrons. So anyhow, the property should be about the same. Similarly. Okay? All right. Let's go back to drift. If you have both, your holes, your electrons, if you apply some of the electrical field, for example, positive here, negative there, so it means what? Holes will move in that direction. Okay. And how about electrons? Will move in the other direction, but the total current is summed up because the current for electrons should be reversed. So they can sum up each other. Okay, you sum up not only the movement of the holes, but also the electrons under the influence of electric field. All right? So it is the proportional constant is called conductivity. And the reverse of conductivity, we call it rho. We call it resistivity. Resistivity, yeah, according to Ohm's law, look like this. Anyway, anyhow, from microelectronics, you will see only by drift instead of diffusion. Okay? The so-called Ohm's law actually depends fully on drift. The drift current composed of holes and electrons. Yeah. For detail, if you are curious, go back to reread your microelectronics. Then I would like to explain a little bit more about the movement of the holes. All right? As I mentioned, nobody here, it doesn't move. It cannot move by itself, but we can expect, some of the valence electrons in the end, we try to fill the hole. Why? Again, you can see that is some kind of electron cloud. Okay? It will show usually for hand plotting or hand drawing, 用手画, 徒手画, we usually have such kind of bond, covalent bond, 共价键. It looks like a chicken leg. but don't expect all those two valence electrons will exist inside the chicken leg. No. According to the electron cloud, they can move even further out of the bond. Okay, look like that. So for some possibility, this will move much closer to the hole. Then you'll say, oh, there is a vacancy. I would like to fill it. I wouldn't like to go back. That's it. Okay? So a student can think, the hole move from here to there. But actually, not by itself, by the feeding of the other valence electron. Okay? And you will tell me, hey, which one? This or that will be easier to fill this hole. Without any influence of the outer environment, the probability should be exactly the same. Okay? So it means what? The hole under balance condition, it can be filled by the top, bottom, right, or left valence electrons with the same probability. That's it. So it can move, it can be filled, and then move here, move there, So totally no net flow. Because it can move with exactly the same probability to the top, to the bottom, to the right, to the left. That's it. So how can you break such kind of balance equilibrium? 你怎么打破平衡? We can apply electric field. For example, positive here, negative there. So if you think holes are positive, then what's the consequence? It will be pushed a little bit rightward, right? Because positive here, negative here, the positive holes will be attracted by the negative terminal, right? Got it? So it means what? It will be easier to be filled by the right valence electrons instead of the left one. Got it? Because it is shifted a little bit to the right. Got it? So it will be much easier to be filled by this one instead of the other one. So the movement will, on average, to the right. That's it. Okay? Again, for such kind of drift, it needs to wait for the other electrons to fill. So the mobility is much, much lower than free electrons. How much lower? Again, 2.5 to 3 times lower. Okay. So anyway, that is the current summary. We have diffusion, we have drift, all of them. Okay, but in conductor, I promise you, they only have such kind of drift. They don't have diffusion. Because the whole density or the electron density on average will be the same for the whole conductor. Even for pure semiconductor, I promise you, the same. So how to make diffusion current effective? It needs the help of our humankind. Okay? How? Oh, very easy. I told you, we can dope different impurity into the pure semiconductor. We can make it become p-type. We can make it become n-type. So if you combine both p-type and n-type, congratulations. For p, here you have a lot of holes. For n, you have a lot of electrons. So diffusion will happen when p-type semiconductor meets n-type semiconductor. Got it? Got it? On Earth, by nature, it's really hard to generate such kind of diffusion current. But by man-made, we can make it. All right, so let's have a brief break here.